Hey everyone, welcome to this explainer. Today we are going to demystify exactly how Linux handles process creation. So let's just dive right in and crack the code.
Quick look at our roadmap to dissect this C program's logic. We'll set up the program, explore the magic of the fork command, peek inside the child and parent processes, talk about concurrency and output order, and finish up with the ultimate process test.
All right, step 1, setting up the program and its prerequisites. You know that every C program kicks off from main, right? But before we even get there, we absolutely need to include two specific header files. First up is stdio.h. This gives us our standard input and output functions. Basically, if you want to print anything to the screen, you gotta have it. The second one is unistd.h, and this is the real star of the show today. It provides the core Unix and Linux system calls. Without it, our compiler would be totally lost when we try to clone our processes.
Which brings us to our first critical variable type, PID-T. When we declare variables to hold our process identifiers, we use PID-T. It's a special data type built exclusively for process IDs in Linux. Honestly, you can just think of it like a standard integer, but one that's specifically engineered by the system to safely and accurately handle these process identifiers.
Moving on to part 2, the magic of the fork command and process creation.
This is where things get wild. Before execution, it's super simple. Just one single process moving forward. But the absolute millisecond that fork command runs, the system clones it. It literally creates an exact copy. So after execution, boom, we instantly have two entirely separate processes, both executing the exact same program simultaneously. It's like our single timeline instantly splits into two concurrent realities.
Now, here is the absolutely crucial point. While the exact same line of code executes in both processes, it returns different values. That's how the program figures out which timeline it's actually in. In the original parent process, the fork command hands back the actual process ID of the newly created child. Let's use 3501 as an example. But over in that newly cloned child process, that exact same fork command will always, without fail, return a flat 0. Okay, let's look at part 3, inside the child process, where our PID variable equals 0. Think about the logic happening here. The program essentially asks, hey, did the fork command hand me a 0? Well, for the child process, the answer is definitively yes. Because it got that 0, the if statement evaluates to true. So the child process confidently marches right into this specific block of code, totally isolating its actions from whatever the parent is doing.
Inside this block, it gets really fascinating. The child can use two specific system functions to figure out who it is and who created it. First, it calls getPID, which just returns the process ID of the currently executing process. Since the child is the one asking, it gets back 3501. Then it uses getPPID. Notice that extra P in there? That stands for parent. By calling this, the child looks up the chain of command and accurately identifies process 3500 as the entity that spawned it.
All right, jumping over to part 4, inside the parent process and its else block execution.
Rewind a second to that logical fork in the road. When the parent asks, did the fork command hand me a 0, its answer is no. Remember, it received the child's ID, 3501. Because that initial condition evaluates to false, the parent completely skips over the child's code and drops straight into the else block. This ensures it only executes its own designated instructions. Once inside this block, the parent calls getPID and gets its own identifier, 3500. But here's the cool part. To find its child, it doesn't even need a special function. It just looks at that PID variable where it stored the return value from the fork command earlier. That variable securely holds 3501, proving the parent knows exactly who its child is.
Part 5, Concurrency and Output Order. Let's look at the execution timeline.
So right at that definitive split point, the fork executes. Moving to step 2, we now have our parent and child running concurrently. They are executing simultaneously from the line immediately following the fork. Then, at step 3, the Linux scheduler steps in. It is solely responsible for deciding which of these two independent processes actually gets the CPU's processing time first.
Now you might be wondering, why does the child sometimes print to the screen first and other times the parent does? Well, because the Linux scheduler allocates CPU time dynamically, either outcome is perfectly valid. The output order changes organically simply because both processes are racing for CPU time. The scheduler makes the final dynamic call on who goes first, so there's really no strict guarantee. Both outcomes are absolutely correct.
Finally, part 6, the ultimate process test visualization. Let's see if you got this down.
Imagine we've just written this out on a classroom whiteboard. The parent process has a PID of 3500. The newly created child process has a PID of 3501. I want you to lock these two numbers into your mind right now because I'm going to ask you 4 rapid-fire questions to test your understanding of exactly what these processes know. Ready?
Question 1. What will get PID ID return in the child? Well, since it's asking for its own ID, the answer is exactly 3501. The child knows its own identity.
Question 2. What will get PPID return in the child? Remember that extra P. When the child looks upward to identify its creator, it successfully returns 3500. It's fully aware of the parent process that cloned it. Question 3. What is the value of the PID variable in the parent? Think back to the magic of the return value. The parent was handed the child's ID, making this value 3501. The parent stored exactly what fork handed back to it.
And finally, question 4. What is the value of the PID variable in the child? This is the ultimate proof of the timeline split. The child's stored variable is always exactly 0. That 0 is the fundamental mechanism that allows the child to know it is, in fact, the child.
So you've conquered the logic of the fork command today. We've seen how perfectly these two processes spin up and identify each other. But operating systems are incredibly dynamic. What happens if that parent process, process 3500, suddenly finishes its work and terminates, but process 3501, the child, is still busy processing? Does the system just abandon it? Does it become what we call a zombie process? These are the kinds of brilliant edge cases that make mastering Linux process management so vital. Think about that final question and keep exploring. Thanks for joining me for this explainer.